definition of continuous function? Well, if you go to any math classes, for every epsilon there is a delta. That's the continuity definition. You can get it from Wikipedia. The continuity definition. The definition of a compact manifold. The definition of a globally stable point, which is from any point in the space you will go to that point. The definition of asymptotically stable. The definition of equilibrium point. Just these 5 definitions side by side, and when you look at them simultaneously, you see, oh, there is contradiction. They cannot come with each other. There is contradiction, which means this can never happen. So it's a very important result. You should never aspire to achieve global stability for your system if you have rotational degrees of freedom and the system is continuous, using continuous feedback. You can do it using discontinuous feedback, that's fine. So, okay, but we did it in our undergrad. And this is very convincing. What went wrong here? What was the problem? Why we cannot achieve that? I mean, we already almost it's almost that we achieved it. What happened? What went wrong? This is the point. When you designed your control law in our undergrad, we designed as if theta is a real number. I just told you that theta really is not a real number. Theta belongs to S1, the circle line. So this control law is not well defined on the real estate space, S1 cross R. What do you mean not well defined? Well, this is a function. Control law, what's the definition of control law? Control law takes measurements, theta and omega, and gives you the control input history that you need to apply at this time. So it takes theta and omega and gives you u. Okay, so this is a function that takes 2 inputs and gives you an output. What do you mean by a function that is not well defined? A function is not well defined when you give it the same point and get different answer. Whenever you give the same point, you should get the same answer. Otherwise, the function is not well defined, right? Okay, here is the thing. This is a point in the set space, theta and omega. Theta is 0 and any omega, it doesn't matter. This point in the state space, theta is 2 pi and the same omega. These 2 points, theta is 0 and theta is 2 pi and the same omega, they are the same point on that state space. Whereas, obviously, if you plug here theta equals 0, or you plug here theta equals 2 pi, you'll get a different number for u, right? So indeed, this function is not well defined on the real estate space. It's well defined where? If you replace this guy by r, which is very subtle, but it will affect you. Okay, well now we're a little bit convinced, but what will happen in reality? Still, you cannot digest it very well. Because we really did it in our undergrad, thinking that we got the best result ever. What's the best result ever? This is the best result in control theory ever. It's globally, asymptotically, exponentially stable equilibrium. This is the best result that you can aspire for. Okay, now what we have, this is not well defined. What we have is something called the unwinding phenomenon, which is this your spacecraft or whatever, maybe give it just a little bit disturbance, maybe -5 degrees. It depends on the initialization of your measurement for theta. And your controllers, because your controller might think that this is really -5 degrees and I will do this corrective action, or it might think that it's all the way -5 degrees, for which how it will respond, it will come back. So you have just a little bit few degrees. Any smart controller will just give you this few degrees back. Your controller might confuse and do all the way to get to the other side. Which means that we don't have a proof for near stability, the Lyapunov of stability. You know this hierarchy, we have here, that's okay. You have Lyapunov stability, which is just near stability, which is you will not blow up. And then you have asymptotic stability, which, okay, I will not blow up, but I will even go to my desired equilibrium point. And then you have exponential. Now I will go, not eventually, but exponentially fast. And you have global, which is from any point in the space, I will go exponentially fast. We thought that we achieved the best ever, and now we lose the mere Lyapunov stability. We don't have mere Lyapunov stability. Why? Because my system is not bounded. You can give it just a 5-degree disturbance, and it will have like 355 degrees, response. So this is the unwinding phenomenon. Okay. That's okay. let's see it for real examples. Spacecraft attitude control. What was the impact of this result? This result is recent, right? It is like 2000, yeah? Okay, relatively recent. Because people tried to do spacecraft attitude from a time. How we write down our equations for motion sometimes confine the way you do control. So typically, spacecraft we have just the 3 degrees of freedom, right? And if we do that, how are we going to write down equations? Well, we have many representations, but one of the most common representations was Euler angles, which we studied in mechanics, aerodynamics. Of course, the Euler angles, by definition, they are local representations. We know that for any representation of the 12 representations of Euler angles, there's going to be always one singularity, right? For the common representation, which is yaw, pitch, roll, we have 90 degrees, the singularity at theta equals 90 degrees, if you remember, right? So it cannot cover the entire slit space. It's essentially local, and you will have always singularities. So that's okay. So if we have this guy, we can do linear control on the Euler angles representation, and we're done. That's right, but this is, like I said, this is essentially local approach. So then people, when they realize that, why we don't use quaternions? Because quaternions, you can use quaternion to represent your spacecraft attitude control. Instead of 3 Euler angles, you have 4 quaternions subject to one constraint. We didn't study it in detail in dynamics. You can go and read about it. It's nothing fancy. But the good thing about it is that it removes your singularity. In the sense, it can represent the entire dynamics of the entire state space. So it's a global representation, okay? Now we have global representation. We hope to aspire for global results. But our linear control theory is essentially, linear means for small neighborhood. Well, we have Liouville theory, right? Which showed up maybe in the 50s or whatever. So we became mature at least. So now we have global representations. We have global theory. We can apply this to that and get global results, right? And yes, in the maybe 80s or something, there are several papers in the most prestigious journals, IEEE Transactions and Automatic Control, under the title of Global Asymptotic Stability of Spacecraft Attitude Control, Attitude Dynamics, using Quaternions feedback. Quaternions feedback approach to blah, blah, blah. Several papers in these very prestigious journals, but we just learned now that this cannot happen, right? I mean, I don't care about your results. And this is the good thing about math, is that, well, this is a necessary condition. I mean, you don't satisfy, then I don't care what you did. I don't care what you did. Your system cannot achieve that, cannot achieve this very fancy type. And yes, they were wrong, and all the ensuing papers, so from this point on, all the papers on spacecraft attitude control, they have the title, even using quaternion, even using Liouville, they have the title of almost global. We can never achieve global. Now all the titles have almost global asymptotic stability. It's an interesting result, interesting story to tell, but you might think, well, okay, we got it. I mean, I can solve this by actually having an if statement in my software saying, well, I will restrict my measurement from negative pi to pi, and I'm done, right? I will not allow my controller to think that it's 355. I'm okay with that. Yes, but your controller will be discontinuous, right? Because if statement means it's discontinuous. That's okay. You can get around it with an engineering solution. I totally agree. If this is not, the thing that you like to learn. And actually will not be the focus of our course. But this is one of the things that will allow you, this is one of the things that you can get when you have the language to read these papers. This is my favorite part, is that, because even if we do local analysis, here is the point. We have actually 3 main engineering questions, usually when we design things, particularly we design controllers, or even not controllers, things in engineering. First of all, can I do it? Can I do this thing? Can I achieve it? Can I go from here to there? Can I design this thing? Does there exist a solution? This is why it's an existence question. Does there exist a solution to your problem? This first. Second, if the solution exists, can I do it optimally? Because we engineers, we like to do things optimally, right? So, and this is the existence of optimal solution. Mathematicians, they care much about existence. We don't care on we jump here. How can I do it optimally? But you know, you shouldn't waste your entire life trying to solve a problem that does not even have a solution, right? I mean, this is why the existence theorems are really useful. Does it exist? Can I do it? If yes, okay, can I do it optimally? Because the fact that you are able to do it does not mean that you cannot do it optimally. It might mean that there exists a solution, not necessarily an optimal one. Okay, if there is an optimal solution, then okay, please tell me how to do it, and this is the optimal control theory or optimization if you're looking about general design. So controllability, we're saying nonlinear controllability in the title, so controllability has to do with the very first question, existence. Does there exist a solution to your problem? Can I go from this point to that point in finite time? Can I go or not? So controllability in an existence solution for linear systems. So this is the definition. This system is controllable if there exists a control U that steers the system from any point to the origin for the linear system. And actually, if you can go to the origin, you can go to any other point. So for linear systems, basically, it's can I go from any point to any other point? Okay. How many of you guys did take 270A? 270A? Okay, because I mean it's not requirement here, but you know it will be hard to appreciate the nonlinear control without